Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this topic today, I want to discuss about thin cylinders. So the course outcome of this topic is analyze the stresses developed and deformation of thin and thick cylinders due to internal pressure. So whenever the cylinder is subjected to some internal pressure, so what are the stresses induced in the cylinder we will analyze, and then we will derive equations for different cylinders. So introduction to thin cylinders. So what do you mean by thin cylinders? So this unit presents the analysis of thin and thick cylindrical shells subjected to fluid pressure. Like example, steam boilers, reservoirs, reactors, nuclear containers, tanks, working chambers of engines, etc. are the common examples. These all are thin cylinders. So in this unit, the stresses and strains induced in the walls of a cylinder will be found out based on the geometry of the shell and equilibrium of the forces involved. So now we shall begin by defining a thin cylinder, identifying the assumptions made in this analysis. After finding the stresses in the material of the cylinder, the strains will be calculated. So what are the stresses induced in the cylinder, and then strains equations we will derive. The stresses in wire-wound pipes will be considered. We shall then see the limitations for treating a shell to be thin and look for the differences in the behavior of a thick shell as against a thin shell. So we will first begin with defining the thin cylinder and then assumptions. So the following assumptions are made in order to derive the expressions for the stresses and strains in thin cylinders. So one is the diameter of the cylinder is more than 20 times the thickness of the shell. That case, it is said to be thin cylinder. So the stresses are uniformly distributed throughout the thickness of the wall. The stresses are uniformly. And first condition, diameter of the cylinder is more than the 20 times of the thickness. The D is 20 times of the thickness of the cylinder. So the following assumptions are made in order to derive the expressions for the stresses, the strains in the cylinder. Already we have seen A and B 2 points. The another assumptions are the ends of the cylindrical shell are not supported from sides. And fourth one is the weight of the cylinder and that of the fluid contained inside are not taken into account. The weight of the cylinder is not considering. Whatever containing this fluid or gas inside the cylinder. While deriving equations, we are calculating the problems, we are not taken into account. So these are the assumptions. Based on these assumptions, made some equations. The atmosphere pressure is taken as the reference pressure. The atmospheric pressure has taken as a reference pressure. So here see the cylindrical vessel with hemispherical ends. So let us now consider the vessel with hemispherical ends. The wall thickness of the cylindrical and hemispherical portion is different. The thickness of the wall is different for the semi-spherical ends. So while the internal diameter of both the portions is assumed to be equal, so that the cylindrical vessel is subject to an internal pressure P, let us assume. So in this diagram shown, these are the ends and wall. So here shown this wall thickness is T1. Here hemispherical ends are thickness is T2. So the internal diameter is D. So whenever this cylinder containing fluid or gas inside, so acting the internal pressure on these walls and the cylindrical ends. First we will see what are the stresses induced for the cylindrical portion. So here whoop or circumferential stress sigma C or sigma H. Whoop or circumferential stress. So that is PD by 2T1. So what is P? That is the internal pressure and the diameter of the cylinder and then thickness of the wall T1. Similarly, longitudinal stress, that is sigma L, PD by 4T1. So whoop or circumferential strain, so apply this equation, so we will get PD by 41 into E into 2 minus mu. So here the sigma to epsilon 2, the whoop or circumferential strain you can write in terms of Poisson's ratio, PD by 41 E into 2 minus mu. For the hemispherical ends, take a section, cross section of hemispherical shell. So you can see the internal diameter and whoop stress, and then T2 and the small portion of the hemispherical shell. For the hemispherical ends, the symmetry of the sphere, the stresses set up owing to internal pressure will be two mutually perpendicular whoops or circumferential stresses of equal values. So again, the radial stresses are neglected in comparison to the whoop stresses, as with this cylinder having thickness to diameter less than 20. So when compared to the whoop stress, we are not considering radial stresses. So the radial stresses are very small values will have, so that we can omit. So consider the equilibrium of the half sphere. Force on half sphere owing to internal pressure is equal to pressure multiplied with projected area. So projected area, pressure into pi by 4 into d square. And then resisting force, stress multiplied with area. So area here pi d into T2. So this resisting force is equal to the internal pressure. So that is P into pi by 4 into d square is equal to this one, sigma h into pi d into T2. So that for sphere, we can calculate the whoop stress is equal to PD by 4T. So P internal pressure and diameter of the hemispherical shell, and then T2 is the thickness of the hemispherical ends. Similarly, the hoop strain. So PD by 40 T2 into E into 1 minus mu. So substitute this equation and then simplify. So here shown the diagram, the hemispherical ends shown in dotted lines. So the dotted lines are increased in their dimension. So cylindrical walls, whenever this hemispherical internal pressure induced, the cylindrical hemispherical ends will increase the diameter. And similarly, here shown here length, the changes, the dimension changes after stresses induced. So for the cylindrical portion of the spherical ends to expand by different amount under the action of internal pressure. So owing to difference in stress, the two portions, the cylindrical and spherical ends, expand by a different amount. The cylindrical and spherical ends. So this is cylindrical and spherical ends are expand by a different way. So this incompatibility of deformations causes a local bending and shearing stresses in the neighborhood of the joint. Since there must be physical continuity between the hands and the cylindrical portion. For this reason, properly curved ends must be used for pressure vessels. See, here equating the two strains in order to, there shall be no distortion of the junction. The strain at the cylindrical wall PD by 41 into E into 2 minus mu, and similarly the hemispherical ends, the spherical ends PD by 40 into E into 1 minus mu. So equate these two strains. So we will get the thickness ratio in terms of T2 by T1 is equal to 1 minus mu by 2 minus mu. So general steel works, the mu is 0.3, therefore the thickness ratio becomes T2 by T1 is equal to 0.7 by 1.7, or T1 is equal to 2.4 times of T2. So the thickness of the cylinder walls must be approximately 2.4 times that the hemispheroid ends for no distortion of the junction to occur. So the T1 by T2 is equal to 2.4. So up to now, what we have calculated summary given here. So let us summarize the derived results. The stresses set up in the walls of a thin cylinder owing to an internal pressure P are given circumferential or hoop stress. So that is SHR sigma H. Longitudinal and axial stress, sigma L is equal to PD by 40. So where D is the internal diameter and T is the wall thickness of the cylinder, then longitudinal strain you can calculate by using this relation. 1 by E into sigma L minus mu into sigma H. The hoop strain is 1 by E into sigma H minus mu sigma L. The change of internal volume of cylinder under pressure can write equation PD by 40 into E to 5 minus 4 V into volumetric strain, V volume. So from thin spheres, circumferential or hoop stress is PD by 40, already you know. So here we'll see the change in volume. The change in volume of a thin cylindrical shell due to an internal pressure. So there is always an increase in the length and diameter of a thin cylindrical shell due to an internal pressure. So already we have seen in previous slides. So whenever the cylinder is subjected to some internal pressure, so there is always some increase and length and diameter will vary the dimensions due to an internal pressure. A little consultation will show that increase in the length and diameter of the shell will also increase its volume. So whenever these two are increases, so then the increase in volume also will increase. Now consider thin cylindrical shell subject to an internal pressure. So how do we calculate the volume? We will see. Let original length of the length L and D is the original diameter, and delta L is change in length due to pressure, and diameter is change in diameter due to pressure. The volumetric strain is defined as change in volume divided by original volume. So what are the change in volume? To the original volume. So that is epsilon V delta V by V. So the change in volume is equal to final volume minus original volume. The original volume V is area of cylindrical shell into length. So that is pi by 4 into d square into L. So the final volume is equal to final area of the cross section into final length. So what is the final length? L plus delta L. Original length plus the change in length. Similarly, the diameter and the change in diameter. So now, by neglecting smaller quantities, the final value you can write like this. Pi by 4 into d square into L plus 2d into L into dt delta d plus delta L into d square. So the change in volume, you can write pi by 4 into 2d into L into delta d plus delta L into d square. So the volumetric strain, delta V by V. So delta V, so already we have derived in the previous slide. 5 by 4 into 2d into L into delta d plus delta L into d square. So divided by 5 by 4 into d square into L. So we will get the final equation epsilon c plus epsilon L. So here the epsilon c is circumferential strain and longitudinal strain. So finally delta V you can write in terms of circumferential strain plus longitudinal strain. So these are the empirical relations for the change in volume of a thin cylindrical shell due to an internal pressure. So these are the references I have taken. It's Ramamurthu, and title of the book is Strength of Materials, and publishers are Dhanapati Rai Publishing Company, and R.K. Bansal, author name, and the title of the book is Textbook of Strength of Materials, and publications are Lakshmi Publications, and R.S. Kurmi and Gupta, that is Strength of Materials, and Chand and co-publishers, and then we have taken the NPTEL lecture notes, the Strength of Materials. So therefore any one textbook for other more clarification. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.